cardiovascular system, it's really composed of three subparts, and we're going to look at each subpart individually. Cardiovascular system is the blood, the heart, and the blood vessels. Those are the three parts. After we do just a little bit of orientation, we're going to do the blood first, then we'll do the heart, and we'll do the blood vessels. So that's kind of where we're heading. When we look at the cardiovascular system, we know that there's a number of different vital functions, very important functions. Probably the one we think of most is delivering oxygen to the cells. We know that if we don't deliver oxygen promptly and in great enough quantities to the cells, especially the cells that are most energy using, like the brain and the kidneys and some things like the heart itself, that we could die within four minutes or so, start to die at least, and shortly after that. And so the oxygen that is needed for cell respiration in order to create enough ATP, we could make some anaerobically, but not enough to really sustain us for very long. So that oxygen delivery is absolutely critical. This is why if we lose too much blood or if we get a blockage in our blood vessels, it's a big deal, because then cells in that area can start to die. If we get a blockage in the brain, it's a stroke. If we get a blockage in the heart, it's a myocardial infarction or a heart attack, for instance. So delivering oxygen. Coupled with that, the blood also transports carbon dioxide in the other direction, if you will. Oxygen comes from the lungs to the cells. Carbon dioxide is a byproduct of cell respiration, as we know, and it's being delivered from the cells to the lungs so we can breathe it out. So gas exchange and gas transport, primarily oxygen and carbon dioxide, is a major function of the cardiovascular system. In addition, the blood transports a lot of other things that are needed. Nutrients. How do we get the nutrients from the digestive tract where they're absorbed to the cells, through the blood, through the blood and the blood vessels? All right. How do we get the waste products and take it to the kidneys so they can be eliminated through the blood? How do we help with our body temperature? We can shift blood around. If we're cold, we shift it more to our body core. If we're hot, we shift it more to the periphery and to the skin. And so body temperature regulation. How about hormones? We just talked about hormones in great detail. How do the hormones get from where they're made to their target cells? Through the blood. Okay. So all of these are important. We also have some cells that are important for body defense, white blood cells, and they spend time traveling in the blood as well. And blood clotting, which is also an important function, hemostasis, preventing blood loss. Those are some of the major functions that we might think about when we're looking at the cardiovascular or circulatory system. Blood, the heart, look at with the four chambers, and then the blood vessels with the different categories that we'll look at. Coupled with the cardiovascular system, often associated with the immune system, we have the lymphatic system. That transports excessive interstitial fluid back into the blood, and during that pathway back to the blood, it goes through a lot of structures like lymph nodes and things that help in body defense. So the lymphatic system is important in maintaining our fluid balance as well as body defense. Well, let's turn to the first of the three big subcomponents of the cardiovascular system, and that's the blood. When we look at the blood, let's first imagine how much volume of blood we have. Well, some things, quite a bit of things, we need to memorize. And I want to explain one of the reasons I think it's important to memorize certain aspects. And we'll also try to point out, don't worry about memorizing this aspect, you can look it up. Now you might say, well, I can always look up a blood volume. But for much of learning and comprehension and putting things together, I think we need a scaffolding of knowledge in our memory banks that we can tie things to. So I think it's helpful to memorize some values and certain things, and I think blood volume is one of those things that's good to memorize. Now I'll say it's about 5 liters. Some sources say at 5.5. The truth is, it depends on your body size. The smaller you are, the smaller your blood volume. The larger you are, the larger your blood volume. But I think it's nice to have something specific. Let's just say 5 liters, shall we? And that'll be close enough. Now that blood volume is the blood that's in our heart, in our blood vessels, our entire blood capacity. 5 liters, if you think about it, is not that much. If you have a liter bottle, Neil, I think is yours 2 liters?
No, I don't think so.
Liter and a half?
This is a liter and a half.
This is a liter and a half.
1.2 liters.
1.2. Oh, it looks bigger than, anyway. So, if you had 3 of these, you'd be over, right? You'd be about 5.5. So, that's your total blood volume. That's not like a huge amount, is it? And so if we picture it that way, we can't hemorrhage, which is losing the blood, too much. You could have internal hemorrhage or external hemorrhage. So we need to, so that's about our blood volume. Now, when we look at the blood, we know that the blood is composed of a number of different things. It's composed of what we call formed elements, which we subdivide, and plasma. Now, first of all, the term formed elements sounds kind of silly. You haven't heard that term for any other thing. Why do they say formed elements? This is essentially the cells and the cell fragments in the blood. Why don't they just say cells? Because it's cells and cell fragments, and even the cells are not really, some of them are not really true cells. So we call them this odd term, formed elements. We have 3 types. Erythrocytes, also called red blood cells, as you probably are aware. Leukocytes, also called white blood cells, and platelets, also called thrombocytes. Those are our formed elements. We can think of them as cells or cell fragments. Technically, even though erythrocytes have that suffix of site cells, red blood cells are not really true cells. Why? Because they lose all their organelles, right? No nucleus, they can't divide. No mitochondria, they can't do cellular respiration. They're packed full, red blood cells, of hemoglobin, a protein, in their maturity. Now, the precursor cells can divide, and they're formed in the bone marrow, as are all of our blood cells. They're all formed in the bone marrow. But we still call them red blood cells, and we don't worry too much about it. White blood cells are true cells. And we're going to see that there's 5 subtypes of white blood cells. We'll mention those a little later, but there's 5 types of white blood cells, or leukocytes. And those white blood cells are important in immune defense, aren't they? The red blood cells are gas transport, oxygen, and to a lesser extent, carbon dioxide. White blood cells are immune defense. The platelets are in hemostasis, stopping the bleeding, a little bit of clotting. That's their function. Well, what's the plasma? The plasma is the fluid portion of the blood. Now, to help us visualize it, we can take a little blood and we can centrifuge it, spin it down. When we centrifuge our blood, we find that the red blood cells go to the bottom because they're the densest. Then we have a little bumpy coat layer, that's the leukocytes and platelets, and then we have the plasma. And then we can easily visualize that plasma is approximately 55% of the volume of our blood, and the erythrocytes are usually about 45% of our blood volume. Now, less than 1%, we're already at 100%, right, but we're sort of just approximating, less than 1% are our bumpy coat layer, the leukocytes and the platelets. Hematocrit, which is important medically when you're trying to figure out how a patient is doing, what's their hematocrit, is the percentage of the blood that is red blood cells. It's not a quantitative number in the sense of saying you have this many red blood cells. It's the percentage of the blood that is red blood cells. And it varies according to people and all that. But we'll look at the term, we'll memorize the term 45% and realizing that there's some variability and some ranges and all that. But to help give us that scaffolding of learning, we'll say it's 45% of the blood. Now we're going to talk more about the red blood cells in a minute, but I just want to give you another number right now to show you how important the red blood cells are. If you take a drop of blood, the units are millimeters cubed, which is about a drop of blood. There's about 5 million red blood cells in every drop of blood. Ooh, that's a lot, right? Okay. We'll tell you that number again a little later, but it just is to impress on you that the red blood cells make up a pretty good amount of the blood. Well, okay, let's talk about the plasma. The plasma is usually a bit straw colored, and it's mostly water, but it has some other important components in it. It's going to be having a lot of stuff dissolved in the water. Ions like sodium and calcium and chloride and of course potassium. Potassium's higher in the cells, but it's still in the extracellular fluid as well in the plasma. Metabolites, waste products, hormones of course are traveling. Now if you're a polar hormone, hydrophilic, you will dissolve directly in the plasma, right? If you're a non-polar hormone, you will need a protein carrier. You're still dissolved in the plasma, but you're encased in a protein carrier. You're like riding in a submarine, right? You can't just go in there on your own. You have to be encased in something. So that's going to be important. And then antibodies are part of our immune system. They're proteins that are part of our immune system, and they're in the blood as well. You remember that sodium is particularly important in the extracellular fluid, the internal environment, because it keeps getting pumped out of the cells. Chloride is pretty high in the extracellular, and calcium's pretty high too, but sodium is the largest of all of them. Potassium we find there, but it's more, certainly more found in the intracellular. We need to maintain our concentrations of sodium and potassium and chloride and all in a homeostatic level. And we do blood work very often to try to determine somebody's, are they in balance? If they're in balance, that's great. If they have too much sodium, we say they have hypernatremia. If they're too low, they're hyponatremia. If they have too much potassium, they're hypokalemia, etc., right? Now, of course, sodium, we know the chemical symbol Na comes from natrium because we've used S's for all the others like sulfur and silicon and all that. So we use natrium for sodium, Na. So hypernatremia makes more sense when we're talking about sodium and hyponatremia. The same with potassium. We don't use a P. P is for phosphorus and other things. Well, what do we use for potassium? We use the Latin term kalium. And so hyperkalemia, hypokalemia makes a little bit more sense. And that's why we get some of those terms. Now, when we look at the plasma proteins, water is about 90% of the plasma. The rest is stuff that's dissolved in the water. About 8% of our plasma is proteins. These little proteins are dissolved in the plasma. They're polar, they're hydrophilic, and they can dissolve in there without any problem. We have three major categories of proteins. Let's look at each one. The albumins are the most common of the proteins. Let's say about 70% of our plasma proteins are albumins. What are the albumins? What is their major function? They function to maintain the osmotic integrity between the blood and the interstitial fluid. What do? They maintain the osmotic balance or integrity between the blood vessels and the interstitial fluid. How do they do that? Well, albumins, which are proteins, are going to be solutes. They're dissolved in the plasma. If we have a correct balance of solutes in our blood vessels and in our interstitial fluid, then we won't get any net movement of water between those two compartments, between our blood vessels and the interstitial fluid. It'll stay in balance. The albumins in our blood vessels, in our plasma, help keep that osmotic balance. Now, here's a think it through, which I hope will tie this in and help you remember this concept. Albumins, like most plasma proteins, are manufactured in the liver cells. That's where they're made. Then they go into the blood, and that's where they hang out. If you have a liver disease, you may not make enough albumins. You could have cirrhosis of the liver, cancer of the liver, something like that. You lose some function of the liver. You don't have enough albumin in your blood vessels. You don't retain as much fluid now because you don't have as many solutes. The fluid leaks out into your interstitial fluid, and you get too much fluid in your tissue fluid, your interstitial fluid, and you get edema. That's what edema is, right? Too much fluid. So people with liver problems often have some edema. If it's in your abdomen, it's called ascites. That's one of the places where you can get edema. Now, here's another thing to illustrate the point. We use carbohydrates and fats mostly for energy to make our ATP. We use proteins mostly for structure and for purposes like this, right? If somebody's starving to death, in desperation, their body starts using their proteins for energy instead of structure and these osmotic helper things. Therefore, when we see pictures of starving kids or something, a lot of times they look like they have a really big belly. That's not fat, right? That's water. That's water in the wrong place because you don't have as many albumins in your blood vessels, because you're desperately using it for energy so you won't die from starvation. So now you don't retain as much fluid in your blood vessels. It leaks out into your tissue fluid and you get this edema. And this is showing you that you're close to starving to death because you're using your structural proteins and your proteins that keep you in osmotic balance, and you're using those for energy. You're basically digesting yourself at that point in desperation. So that's an idea, and it tells us a bit about the normal role of those humans. Now next we have the globulins, the next big category. We have alpha globulins, beta globulins, and gamma globulins. The alpha and beta globulins mostly transport non-polar substances in the plasma, in the blood, right? If you're gonna transport a steroid hormone or any other non-polar substance, you need a transport protein, a carrier protein. If you're gonna transport T4, you need a carrier protein, right? What are these? They are globulins, alpha and beta globulins. Well, what about gamma globulins? Gamma globulins are also called immunoglobulins or antibodies. That's what they are. They're antibodies. They're immunoglobulins. If you've ever heard of the names of some of the specific subcategories of antibodies, you say Ig, or immunoglobulins, IgE, IgG, IgM, IgD, missed one, IgA, right? Have you ever heard of those? Maybe not. It doesn't really matter, except those are antibodies. They're immunoglobulins, and so they're abbreviated with all these different IgA, IgG. IgG is the most common, IgM, all those kinds, okay? Those are immunoglobulins, and that's what they do. Our last category, we have the albumins, we have the globulins, we have fibrinogen. Fibrinogen is a precursor protein. Remember, a precursor is something that comes before, that is not as functional, and then it can be transformed into something that is more functional. Fibrinogen is a clotting protein. It's going to be involved in clotting, but to be activated, you have to clip it off, and you make it from fibrinogen to fibrin, and that happens through clotting. That's our three major proteins. What about our blood cells or our foreign elements? There's the three categories. Cubic millimeter. This is a table from your book. 5 million red blood cells in about a cubic millimeter, about a drop of blood. How many white blood cells? About 7 to 10,000. I often memorize 10,000 because it's easy to remember. About 10,000. In the same volume, you have 5 million red blood cells. You have about 10,000 white blood cells. You can see there's quite a difference. And then your platelets. Platelets are just little pieces of cells, just little pieces. And we have about 250,000 of those in a drop of blood, a cubic millimeter. We have subtypes of white blood cells. Neutrophils, eosinophils, basophils, monocytes, and lymphocytes. We'll talk about all those. This gives you approximate percentages of these. Here they are. Here's your red blood cell. It has a biconcave disc shape. Here's our white blood cells. You have a nucleus. These are true cells, the white blood cells. You have a nucleus, and then you have a cytoplasm. If they have visible granules in their cytoplasm, we call them granulocytes. We have 3 granulocytes: neutrophils, eosinophils, and basophils. If they don't have real visible granules in their cytoplasm, we call them agranulocytes, A meaning without, you may remember, and that's the monocytes and the lymphocytes. The names of these white blood cells also have something to do with how they stain histologically. With a blood stain like a Giemsa stain or a Wright stain, neutrophils, the granules don't pick up the stain too well. So they're called neutral because they don't pick up either an acidic or a basic stain too well. Eosinophils stain with an acidic stain, eosin. So their granules look kind of reddish, brownish red in their cytoplasm. Basophils, they stain with a basophilic stain. And they are going to stain their granules very dark blue, purple, or dark black. They're going to be that. The monocytes, their granules don't really stain, and lymphocytes, again, don't really stain. Platelets are little pieces of cells, cell fragments, and that's all they are. Erythrocytes have this shape. Now this happens to be an electron micrograph image that was then colorized with a computer, digitally colorized. We understand that we can see red blood cells through a light microscope, but they're not going to look this big. This was done with an electron microscope, which is always black and white, but then you can add color in it, like colorizing an old black and white movie. In this case, you're colorizing the electron micrograph. This is the shape. We call it a biconcave disc shape because there's a depression on both sides. I bet you know or can come up with a rationale of why this is beneficial for red blood cells to have this shape. What is the advantage for red blood cells to have this shape? Do you suppose? They can squeeze. That doesn't account for the biconcave disc shape, but they can be deformed and squeezed, and that is very important. Carry stuff, almost there.
Oh, maximize surface area.
Maximize surface area. We need really efficient gas exchange in and out of the red blood cell, oxygen and carbon dioxide. By having this design shape with the biconcave disc shape, we maximize surface area, we maximize rate of diffusion, oxygen and carbon dioxide in and out of the cell. And that's, now everything you mentioned, being able to be deformed so they can squeeze through and having the ability to carry a lot of hemoglobin and all that's true too as far as the needs of the red blood cell. But the shape is mostly helpful in their surface area characteristics. Now a red blood cell is about 7 to 7.5 microns in diameter. Let's memorize that. 7, let's say. We won't get too picky with you on a test. About 7, right? The reason it's important to know they're about 7 microns is when you look histologically at a blood smear, you're going to have red blood cells throughout it because there's so many of them. If you want to identify white blood cells, part of the way we identify white blood cells is by their size. Well, how do we know the size easily? We compare them to the surrounding red blood cells. If we know the red blood cells are 7 microns, we can sort of figure out how big in diameter, how large the white blood cells are. Is that right? That's what helps us. So 7 microns is another one of those things that might be helpful to know. We know that all the blood cells, red blood cells, white blood cells, and platelets, are produced in the red or active bone marrow. That's where they're produced. They come into the blood. The precursors for red blood cells divide and divide. But when you get to the mature red blood cells, they have lost all of their organelles. No nucleus, no other organelles. That means they can't live very long. They can't divide. So they are only going to live about 4 months, about 120 days on average. Then they're going to be phagocytized as they wear out. Where are they going to be phagocytized? in the spleen and the liver. That destroys them. Where are the new red blood cells coming from? The bone marrow. So we constantly have to make new red blood cells. We have a protein that you're familiar with called hemoglobin. And we have about 280 million hemoglobin protein molecules in every red blood cell. You don't need to memorize that one, okay? There's some things I think are helpful. I give you that number just to show you that that's an impressive amount of hemoglobin. They're packed full of hemoglobin. And remember, you have 4 heme chains, each with the iron, and you have an oxygen molecule that can potentially bind to each of those 4. So you could take 4 oxygen molecules per hemoglobin, 280 million hemoglobins, plus you have 5 million red blood cells in a drop of blood. You see how you can carry a lot of oxygen that way? You don't need to memorize this either, but I want to just say it to be impressive, to impress on our minds. Production of red blood cells is called erythropoiesis. Good name. Happens in the red bone marrow. We produce about 2.5 million red blood cells every second. Oh, we just did 2.5 million. All right. Wow. That means we're removing about that many too on the other end, right? Phagocytizing them. It's regulated by a hormone that you may have looked at a little bit when we did the endocrine system, and that's erythropoietin. You know the nickname for erythropoietin? EPO. Have you ever heard of athletes, distance, endurance athletes taking EPO? That's erythropoietin. What are they trying to do? Increase their amount of red blood cells so they can increase their oxygen binding capacity. Lance Armstrong, the guy who bicycle, he got in a lot of trouble doing that. Eventually admitted to it. He not only took EPO, and like a lot of bicycle, he wasn't the only one. A lot of times before a race, he would give himself a blood transfusion. How would he do that? Well before a race, he'd take some of his own blood, put it in the freezer. Night before the race, you give yourself a blood transfusion. Oh, I've got more endurance now. Another thing, take EPO. Isn't that something, right? Okay, you could do those kind of little tricks. But of course, if you're an athlete racing or doing whatever, that's illegal. You're not supposed to get an edge due to that. But many do. Many have done it. But that's EPO. The old cells are destroyed by phagocytosis in the spleen and the liver. We need iron, because iron's in the hemoglobin. That's where oxygen actually binds. We need vitamin B12 and folic acid. Why do we need these B vitamins? Because these B vitamins help make up some of our nucleic acids for DNA. Now you might say, hey, wait a minute, red blood cells don't have any DNA, they don't have any nucleus. No, but they're precursor cells that are going to be making cells to become red blood cells. They have a lot of DNA. They're dividing in the red bone marrow. And because we're making so many of them, if we don't have coenzymes, the B vitamins, to make some of our components of DNA, some of the nucleic acids, we can't make enough DNA, we can't make enough red blood cells. And so we have to have enough of these coenzymes. Is that okay? Or we didn't lose you on that? Oh, okay. So here we are, we make them in the bone marrow, come out in the blood, they last about 4 months, 120 days, then they get phagocytized. We recycle some of it. We recycle some of the iron, some of the other components. By the way, the reason our urine, one of the reasons our urine is a little bit straw colored, a little yellowish, is because metabolites of hemoglobin, as you break down the hemoglobin. That's also the reason the feces can be brownish. Some of the hemoglobin that's metabolites of hemoglobin. And so that gives color. If we have low oxygen, we stimulate the kidneys to release EPO, erythropoietin. That goes to the bone marrow and stimulates erythropoiesis, and that brings us back into homeostasis. What can cause anemia? Well, anemia is when we decrease our oxygen carrying capacity in the blood. If we have deficiencies of iron, that's going to give us anemia. Vitamin B or folic acid, we've mentioned that helps in DNA synthesis. Let's just keep it simple. One type of anemia called pernicious anemia, that's stretch. One kind of anemia called pernicious anemia is due to the fact that vitamin B12, in order to get absorbed from the small intestine, needs a carrier to get it from the small intestine into the blood, and that carrier is called intrinsic factor. And some people, they don't have enough intrinsic factor, and so they don't absorb enough vitamin B12, so they don't make enough DNA, which impacts the red blood cells the most because we make so many red blood cells, and so they get pernicious anemia. If you don't have enough vitamin B12 in your diet or something, you can also get anemia. Sometimes people that are really having struggles with alcohol to the point where they're just getting most of their calories from alcohol and they're not eating right, you take them in to the emergency room or whatever, you buff them up, you give them a vitamin B12 shot because they're not eating right, because they're getting so many of their calories from wine or something else, you know. And so they're not making enough red blood cells, so they're anemic. So that's one of the challenges that you can get. If your bone marrow is failed due to toxic drugs or cancer, that can be a problem. Blood loss hemorrhage, it could be either internal or external hemorrhage. You're having a problem with secreting enough EPO from your kidneys. Or excessive destruction of erythrocytes. Sickle cell anemia you've all heard of, you've all dealt with the genetics and where the mutation is and all that. In the hemoglobin, sickle cells don't carry oxygen as efficiently as normal cells, and they don't last as long. They get phagocytized earlier. So you lose some of your oxygen carrying capability when you have sickle cell anemia. What about your white blood cells, your leukocytes? They're going to be involved in immune defense. We have the granulocytes. That simply means they have visible cytoplasmic granules under common staining methods. This are the neutrophils, the eosinophils, and basophils. The agranulocytes do not, the monocytes and lymphocytes. Macrophages is really a little bit of a, macrophages don't travel in the blood. Where do they come from? Macrophages are in the tissues. Monocytes travel in the blood. When they leave the blood, monocytes can merge together and form giant, larger cells called macrophages. So we put macrophages in there, but they're not in the blood. They're in the tissues. If you wouldn't mind, let's know these from the most numerous to the least numerous. And we won't worry about the percentages too much. Which are the most numerous? Do you know? Neutrophils by far are the most. So that's number one. They're the most numerous of the white blood cell. What's second? Lymphocytes. Very good. Lymphocytes. What's third? Monocytes. I didn't know. Number three, and then eosinophils and basophils are quite rare. They're less than 1% usually. if you go to the doctor and they do blood cell count, they're looking at your red blood cells, but they're also looking at your white blood cells. It should be around 10,000 per cubic milliliter, right? But they can also do a differential white blood cell count. That's where they're looking at your white blood cell count percentage. And if one of them's high, let's say neutrophil count is higher than usual, they can sort of detect by the function of neutrophils what kind of disease you may have. Neutrophils are particularly active against bacteria infections. They are phagocytic to bacteria. And so if you have a high neutrophil count, higher than normal, you might have a bacterial infection. Now, if you have a high eosinophil count, you might have a parasitic infection. That's worms. Because eosinophils are particularly helpful in fighting parasites. They also help mediate the allergic response, but they are very, they work against parasites. Neutrophils, by the way, they help in bacterial infection fighting, wound healing, and they're usually the first to arrive at an infection site. Basophils, quite rare, they release heparin and histamine. Heparin is an anticoagulant, and histamine attracts other infection-fighting cells to the area. Sometimes they're involved in allergies, so if you get too many basophils, you get too much histamine, your nose runs, your eyes water, you might take antihistamine, right, to try to treat it, okay? That's something that could be part of that. Monocytes, they're also phagocytic, but they travel in the blood, then they leave, and they become macrophages, phagocytic against viruses and bacteria especially. Lymphocytes are part of the adaptive immune response. They can be subdivided in a number of subdivisions, but T lymphocytes and B lymphocytes are their most common. Platelets are little pieces of cell fragments. They come from giant cells called megakaryocytes. Not monocytes, not macrophages. These are megakaryocytes, very different. And they make the platelets. They're important in immune defense. This is just for fun. These are red blood cells. This is a neutrophil, and it's chasing a bacterium for phagocytic purposes.
Neutrophils are white blood cells that hunt and kill bacteria. In this spread, a neutrophil is seen in the midst of red blood cells. Staphylococcus aureus bacteria have been added. The small clump of bacteria release a chemoattractant that is sensed by the neutrophil. The neutrophil becomes polarized and starts chasing the bacteria. The bacteria, bounced around by thermal energy, move in a random path, seeming to avoid their predator. Eventually, the neutrophil catches up with the bacteria and engulfs them by phagocytosis.
Is that fun? That's what really happened. Well, it happened, but not exactly that last part. Okay, let's see. All of our blood cells are manufactured in the bone marrow, the active or red bone marrow. Red blood cells, platelets come from megakaryocytes, and then all these other cells come from other precursor cells. In order for this differentiation and production to occur, we need erythropoietin for erythrocytes, and we need several others for other types of white blood cells or platelets. That just shows you a list of those. One last thing white blood cells, as they mature, get smaller. Red blood cells too. They get smaller and more differentiated. We have a normal white blood cell count of about 10,000. In leukemia, you get a high white blood cell count, 100,000 or more, let's say. And yet, you are less effective at fighting off infection. Why this seeming dichotomy of having more white blood cells, but less function, less of their normal function? What's going on? Do you see?
Is it like kind of how we were discussing earlier with endocrine, how there's, if something's not functioning right, the body produces more of it?
It's really pretty much in that line. What's happening is leukemia, a form of cancer, is taking these precursor cells and it's speeding up their division. So you're making more of them, but they have not been allowed to completely differentiate. So they're less functional, even though you have more of it. So somebody with leukemia has a high white blood cell count, but a lower immune system function. Those kind of things and connections help me remember stuff, so I hope it helps you to remember stuff. But it puts it into some kind of perspective to say, okay, why do we have more white blood cells and yet they're not doing as good a job on that? Okay, have a wonderful week.